In section 3.2, we're going to be talking about measures of dispersion. And I want to begin this by looking at an example with you. So my example is a fish story. And this also comes from the book, but it's a very good problem to kind of get at the point of dispersion. So a fish story. Ethan and Drew went on a 10-day fishing trip. The number of smallmouth bass caught and released by the two boys each day was as follows. So we have Ethan, he caught 9 bass, 24 bass, 8 bass, 9 bass, 5 bass, and so on. Drew caught 15 bass, 2 bass, 3 bass, and so on. So I'm asking you to find the population mean for the number of smallmouth bass caught and released per day by each fisherman. Do these values indicate any difference between the two fishermen's catches per day? So I'm treating this data as a population. I'm treating it as a population because it was a 10-day fishing trip and we have 10 data values. So each value is the number of fish that the boy caught on a day. So that's the entire population of data for that fishing trip. So that makes this a population of data. So we're going to find the parameters. Before we find the mean, if I asked you to look at this data and tell me, who do you think's the better fisherman? Is Ethan the better fisherman or is Drew the better fisherman? Let me ask a slightly different question. Who do you think's the more consistent fisherman? Ethan or Drew? Ethan? Ethan's usually in the 8, 9, 10 fish range. Now, there was one time that he had a really good day that day and caught 24. There was one time when he didn't catch as many as normal, just 5, so he had a worse day there. But usually he's in the 8, 9, 10 range. Drew, on the other hand, is kind of a hit and miss fisherman, right? He either has a really good day, 15 fish, or a bad day, 2 fish. And so that's Drew. So definitely, I think we could say Ethan's the more consistent fisherman. Whether he's better or not, I think is debatable. But here's the point. Let's find the means. Now, again, this is a population mean. So I'm going to find mu, because this is a population. I use the mu for the mean. And I'm going to find the mean for Ethan. So I'm just going to put an E down here for Ethan. And I'm going to find mu for Drew. So D for Drew. So in order to find the mean, I need to add up all the data values. So if I add up 9 plus 24 plus 8 plus 9 plus 5 plus 8 plus 9 plus 10 plus 8 plus 10, that adds up to be 100. So over the 10 days, Ethan caught a total of 100 fish. So Ethan's mean is going to be 100 divided by 10. And 100 divided by 10 is 10. So on average, Ethan caught 10 fish per day. Well, what about Drew? Well, if I add up 15 plus 5, that's 20, plus 18 is 38, plus 20 is 58, plus 1's 59, 69, 76, 78, 97, 100. Drew also caught a total of 100 fish. So if I calculate Drew's average, I'm going to take 100 and divide by 10, and that is 10. So Drew also has a mean of 10 fish per day. So here's the deal. Here's my point. We have two clearly different distributions of data. We have a distribution of data that's pretty consistent. And then we have a distribution of data that's not consistent at all. But when we calculate the mean, both have the same mean. So measuring the center, finding the mean of a set of data doesn't do an effective job of describing the distribution completely. It just describes the center, but it doesn't really describe the consistency of the data. So that's the point for this question. Do these values indicate any difference between the two fishermen's catches per day? If I just calculate the means only, then there doesn't appear to be any difference between the two sets of data based just on that measure of center. So the answer to that question is no, there doesn't appear to be any difference based just on the mean. But again, clearly, if we look at the numbers as we're doing here, we clearly see a different picture in the data. So if Ethan and Drew went back and told their friends, hey, I caught an average of 10 fish per day, both of them are telling the truth. But we need more than the description of the center. So what I'm getting at is that we need a way to measure not just the center of the data, we need to come up with a way of measuring the consistency or inconsistency of data. And we call that dispersion or variation. So we may want a measure of dispersion, which is what this section's about, measures of dispersion, or sometimes dispersion is called variation, measures of variation. How do the data vary? So there are three main measures of dispersion that we're going to discuss. I'll write those up here. We're going to talk about the range. That'll be the first one we talked about because it's the simplest. Then we're going to talk about variance. And then we're going to talk about standard deviation. Variance and standard deviation are related to each other. If you find one, you're really finding both. So really, in a sense, we're only doing two things. We're doing range, and then we're doing these two. If you know one, you really know the other. So measures of central tendency alone do not give complete descriptions of data sets. Measures of dispersion are also needed, and dispersion is the degree to which the data are spread out. So again, I use the term consistency. Are the data values really consistent, or are the data values really spread out? Now, if we had a third fisherman here, for example, suppose I had John, and suppose John caught 10 fish, 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 then John would have also caught a total of 100 fish, and John's mean would also be 10 fish. And John would be the epitome of consistency. John really has no dispersion. There's no variation in his fishing at all. He always catches 10. So again, we need to be able to distinguish someone like John from someone like Ethan to someone like Drew. And that's where these measures of dispersion are going to come in. So the first measure of dispersion is the range. A positive of the range, it's really, really, really easy to compute. So the range of a variable is the difference between the largest and the smallest data values. That is the range, which our textbook will denote by the letter R, capital R, that is not universal. There's another statistic that uses R instead called the correlation coefficient. And so we'll talk about that in chapter 4. So I generally will not use R for that because of that purpose. Anyway, it equals the largest value minus the smallest data value. Or I call that the maximum value minus the minimum value. So the largest value minus the smallest value. So my next example, I'm asking you to find the range for Ethan and Drew using the data above. Do these values indicate any difference? So if I'm going to find the range for Ethan, then for Ethan, Ethan's largest value was 24. And his smallest value was 5. So Ethan's range would be 24 minus 5, which would be 19 fish. So Ethan had a range of 19 fish. If I find the range for Drew, Drew's largest catch was 20. So his largest value was 20. His smallest value was 1. And 20 minus 1 also gives us a result of 19 fish. So does the range indicate any difference in Ethan and Drew's set of data? Nope, right? So again, the answer here is no. The range in this particular case does not indicate any difference between Ethan and Drew. So a positive of the range is it's really easy to calculate. A negative of the range is it's not resistant. If you think about it, the range is being computed by the largest and smallest data values. If either one of those values is an extreme, then the range is going to be substantially affected by that extreme. We could probably argue in Ethan's case that this 24 is an extreme. That's more than twice the number of fish he caught on any other day. So that extreme of 24 is making his range much bigger than maybe is a fair description. So the range, easy to calculate, but it's not generally going to be effective for us because it is not resistant. So other measures called variance and standard deviation will be more descriptive. So I want to kind of explain how we go about calculating variance and standard deviation. So I've got a couple of tables set up here for this purpose for us. So statisticians were like, we need to have some kind of a measure that describes the dispersion of a set of data. The range doesn't work real well for us because of the fact it's so non-resistant. So they scratched their head and worked on it and finally decided, maybe the best way to describe the dispersion of a set of data would be to come up with some kind of a calculation that involves every data value in the same way that the mean does. So like when we calculate the mean, we add up all the data values, right? And get the total, and then we divide by the number of data values to get what's happening on average. Well, could we do the same kind of thing for a measure of dispersion? And the answer to that is yes. So right here, I've just rewritten Ethan's data, and here I've rewritten Drew's data. And so what statisticians kind of decided is they said, well, let's see how far each data value deviates from the center. So if the center is the mean, and remember, Ethan had a mean of 10 fish. So if the mean is 10, let's find the difference between each data value and the mean. So in other words, Ethan this day caught 9 fish. Let's take 9 minus 10. Well, 9 minus 10 is -1. That first day, Ethan was 1 fish below average. So that -1 indicates 1 fish below average. That was the deviation. This day, 24 fish. Well, 24 minus 10, that's 14. That day, Ethan was 14 fish above average, above the center. 8 minus 10, -2. That day, he was 2 fish below average. 9 minus 10, -1, 1 fish below average. 5 minus 10, -5, 5 fish below average. 8 minus 10, -2. 9 minus 10, -1. This day, 10 minus 10, that's 0. That day, he did not deviate from average at all. He was average. 8 minus 10, -2 fish below average. 10 minus 10, he didn't deviate from average at all that day. So what I have calculated right here, again, x sub I minus mu. So I'm taking each data value minus the mean. And again, that's giving me the deviations. How does the data values deviate from the center? Now, the original idea was to try to find an average of that. So if we were to try to average these deviations, that would give us maybe a judgment of how the data is spread out, how it deviates from the center. The trouble is, if you add up -1, 14, -2, -1, -5, -2, -1, 0, -2, and 0, if you add all of those up, the result is 0. The negatives and the positives cancel out, giving a result of 0. And the sad thing is that always is going to happen. So about half of the data values are going to be below average, which is going to give negative deviations, and about half of the data values are going to be above average, which is going to give you positive deviations. And so when you combine those, that's going to cancel out and give you 0. So that didn't work. In fact, if we do the same thing for Drew, and you can check this, I'm telling you these add to be 0, you can check me, they do. The same thing happens for Drew. If I take 15 minus Drew's average was 10 fish also. That was Ethan's. So if I take 15 minus 10, that's 5. So he was 5 fish above average that day. 2 minus 10, that's -8. He was 8 fish below average. 3 minus 10, -7. 18 minus 10, +8. 20 minus 10, +10. 1 minus 10 is -9. 17 minus 10 is 7. 2 minus 10 is -8. 19 minus 10 is 9. 3 minus 10 is -7. And if you add all of those up, and you can double check me, but that adds up to be 0 as well. Again, because about half of the values are negative and half of the values are positive, and they cancel out. That always happens. So that didn't work for a measure of dispersion. We couldn't find an average because we always get 0. So statisticians scratched their heads again, and they decide, what can we do about the fact that the negatives and the positives are going to cancel out? Well, one thing they decided is, well, what if we took the absolute value of all of these values? So what if I took the absolute value of -1? That would be 1. And if I took the absolute value of 14, that would be 14, and so on, and average that. And that actually is a statistical calculation, but it turns out not to be particularly useful. So instead, what statisticians decided is, what if we take all of these deviations and square them? If you square a negative number, you get a positive. And if you square a positive number, you get a positive. So squaring will remove all the negatives. So if I square -1, the result will be +1. If I square 14, 14 squared is 196. If I square -2, that's 4. If I square -1, that's 1. If I square -5, that's 25. If I square -2, that's 4. If I square -1, that's 1. If I square 0, that's 0. If I square -2, that's 4. If I square 0, that's 0. So if we add that up, and incidentally, what I have calculated here, I've labeled over here in the left of the table. That is each data value minus the mean. So that's the deviations. And then I'm squaring that. So if I add that up, 196 and 4 is 200, 225, 1 and 5 makes 230, 232, 236, I think. That is 236. So I'm going to write that over here. So that 236, that is the sum of x sub I minus mu squared. So if we take the 236 and we divide that by 10, the number of data values, that is equal to 23.6. And that calculation right there, 23.6, is called the variance. Specifically, this is called the population variance. It's the population variance because we have a population of data. Now, if I do the same kind of thing for Drew, if I take Drew's deviations and square them, so 5 squared would be 25. Negative 8 squared would be 64. Negative 7 squared would be 49. 8 squared, 64. 10 squared is 100. Negative 9 squared is 81. 7 squared is 49. Negative 8 squared is 64. 9 squared is 81. Negative 7 squared is 49. So if I add those up, and I know I don't have my calculator on the camera, but I'm just going to add up these 10 values. So 25 plus 64 plus 49 plus 64 plus 100 plus 81 plus 49 plus 64 plus 81 plus 49, that adds up to be 626. So 626. And so for Drew, that is his sum of x of I minus mu squared. So Drew's population variance is going to equal 626 divided by 10, which is 62.6. So this variance, what it's going to do is it's going to show us how the data is dispersed on average. So essentially, the larger the number, the more spread out the data are, the more dispersion there is in the data. So finally, between Ethan and Drew, we finally have a difference in the description. Ethan has a variance of 23.6. Drew has a variance of 62.6. The fact that Drew's is 62.6 compared to Ethan's 23.6 means that Drew's data is more dispersed. It's more spread out. It's less consistent. So this is a measure of how spread out the data is going to be. Now, just for the sake of saying it, I said, what if we had a third fisherman, John, who always got 10 fish a day? Well, if I found John's deviations, 10 minus 10 would be 0. 10 minus 10 would be 0. 0, 0, 0, 0, 0, 0, 0, 0. So if I did this for John and I added up all of his deviations squared, you square 0, you still get 0. John would have a variance of 0. A variance of 0 would mean you don't really have any dispersion. You have the same value repeated over and over and over again. So a variance of 0 means no dispersion at all. Now, in real data, that's not generally going to happen, right? So variance is really, really good. But there's one problem with variance: the units. So I want to think about the units. So when we calculated Ethan's and Drew's means, the units here are fish, or if you prefer, you could say bass. So on average, Ethan caught 10 fish. On average, Drew caught 10 fish. So here's the deal. When I take 9 fish minus 10 fish, I get -1 fish. So the units right there would be fish, right? -1 fish. When I take 24 fish minus 10 fish, that gives me 14 fish. 8 fish minus 10 fish is -2 fish, and so on. So the units here are all fish in this row. But then when I square that, if I square -1 fish, I get 1 square fish. When I square 14 fish, I get 196 square fish, and so on. 4 square fish, 1 square fish, 25 square fish, and so on. So when I add that all up, I have 236 square fish. Do you see an issue with that in the units? What in the world is a square fish? There's no such thing. It doesn't make any sense. So then when I take 236 square fish and divide by 10, my variance is 23.6 square fish. So the only real problem with variance is I get these square units that don't really make sense, like square fish. And incidentally, the same thing would happen to Drew. 15 fish minus 10 fish would be 5 fish. And if I square that, I get 25 square fish. 2 fish minus 10 fish would be negative 8 fish. Square that, 64 square fish. So when I add this all up, that's 626 square fish. And if I take 626 square fish and divide by 10, that's 62.6 square fish. Again, the units don't make any sense. So statisticians were like, wow, we love this variance thing, but square fish, that doesn't make any sense. What could we possibly do to not have such weird units? So statisticians said, hey, to get back to fish, let's just take the square root of this variance. So if I take the square root of 23.6 square fish, the square root of 23.6, that is 4.858 if I round to 3 places, 4.858. This is approximately 4.858 fish. And if I do the same thing for Drew, if I take the square root of 62.6 square fish, the square root of 62.6 is 7.912, so 7.912 fish. Now this calculation, when I take the square root of the variance, is called the standard deviation. And specifically, this is the population standard deviation. So I'm not going to write it here. Well, I guess I will. I'm just going to abbreviate for Drew. That's the population standard deviation. So Ethan's standard deviation is 4.858 fish. Drew's standard deviation is 7.912 fish. It works kind of the same way that the variance works, except we have nicer units. The larger the standard deviation, that would indicate there's more spread in the data. The smaller the standard deviation, the less spread there would be in the data. So like John up here, if I found his standard deviation would be 0, indicating there's 0 spread in the data. So as a general rule, the larger the standard deviation, the more dispersed the data are. The smaller the standard deviation, the less dispersed the data are. And we're back to good units, the units that we have in our data. Now I do need to point out, I said the larger the standard deviation, the more spread out the data are, the smaller, the less spread out they are. I will say you do have to also take into consideration the size of the data. So if these data values here, instead of being 9, 24, and so on, if I were to multiply all of those, say by 100, if this was 900 and 2400 and 800 and 900 and 500 and so on, then the fact that those data are in the hundreds instead of just like single digits mostly is going to give me a larger standard deviation. So bigger data is going to have bigger standard deviation just because the numbers are bigger. So don't lose sight of that. When I'm saying that the larger the standard deviation, the more spread out the data is, that is true as long as we're talking about data sets that have the relative same size. It wouldn't be fair to compare, say, like a commercial fisherman's catches, which would be in the hundreds probably, to a single fisherman whose data is not going to be in the hundreds. Clearly, the commercial fisherman is going to have a larger standard deviation because it has larger number of catches. Definition: the population standard deviation of a variable is the square root of the sum of squared deviations about the population mean divided by the number of observations in the population, N. So if you just read that sentence, that sounds like a horrible sentence. What did I just read? Well, it's what I'm talking about, right? So it's the square root, we're square rooting to get back to fish, of the sum of the squared deviations. So we're squaring all of the deviations and adding them up. And then we're dividing by the number of observations. In other words, we're finding the average of the squared deviations, again, because of the whole negative deal. So we're averaging the squared deviations, and then we're square rooting that to get back to regular units. That is, it is the square root of the mean of the squared deviations about the population mean. So in other words, symbolically, the population standard deviation is symbolically represented by this symbol right here. It kind of looks like an O with a curly Q on it. That is the Greek letter sigma, and specifically it is lowercase sigma. So you kind of write that, at least I do. I start up the top and circle around and then put the curl on it. I'll do it on this side again. So start up top, come up and put the curl on it. That is sigma. Sigma, I told you the other day, is kind of like S in our alphabet. So in the Greek alphabet, sigma is kind of like S. So sigma is for standard deviation because standard deviation starts with an S. Now again, the other day, I also told you that this is sigma. But the difference is this is like uppercase sigma, and that stands for sum, like adding. And this is lowercase sigma, standard deviation. This symbol is pretty universal. So it doesn't matter what resource you look at, typically if they use sigma, it stands for standard deviation. As before, we may use like a subscript behind it, like sigma sub x. That would mean that is the standard deviation of the x variable, as opposed to sigma sub y would be the standard deviation of the y variable. So let's pick apart this formula. So sigma equals the square root. We talked about that. We're going to take the first data value minus the mean, and we're going to square it. Then plus, we're going to take the second data value minus the mean, and we're going to square it. And we're going to take the third data value minus the mean, and we're going to square it. And we're going to keep doing that and adding it up until we get to the last data value minus the mean and square it. So that is the deviation squared, and we're averaging the squares of the deviations. So we're adding those up, we're dividing by n, and then we're taking the square root to get back to regular units. Or we can abbreviate that notation using the sigma. So here I have sigma, again, that means I'm adding up, parentheses, x sub I, so that's the data value, minus the mean squared. So I'm taking each data value minus the mean, squaring the result, and then adding all of those things up, divided by n, and then taking the square root. Again, it looks horrible, but when you understand what it's saying, it's really not so bad. This formula right here is referred to as the conceptual formula for population standard deviation. It's conceptual formula. It's really what's going on. We're seeing how far each data value is from the mean. That's the deviations. We're squaring it. We're finding the average of that, and then square root again to get back to regular units. It turns out that if you had to do all of this stuff by hand, and you didn't have technology to do these calculations for you, there is actually an easier computational formula that can be used. Now, in this class, once I show you a couple of examples, as a general rule, we're going to use technology. So the computational formula is not going to really be a huge benefit for us, but I do want to demonstrate it for you. So this formula right here is the computational formula. And so if I use this formula, it makes my computations a little easier than having to do all of this work like we did on this problem. Now, I picked this particular problem because everything works out nice. The mean is a nice, neat number, 10, no decimals. All the data values are nice numbers, 9, 8, 5, 24, all nice numbers. So that when I take the data value minus the mean, I always get a nice, neat number, -1. positive 14, negative 2, and so on. So that then when I square it, I get nice, neat numbers. Everything works out beautifully here. But most of the time, when we find a mean, it's not going to be nice. The mean might be like a decimal, a nasty decimal. And then even doing something as simple as subtracting becomes kind of nasty because of the fact that you're dealing with the decimals. And then you have to square those decimals, which makes it even nastier. And then you have to add those up and divide by the number of data values. Again, nasty. So we can usually avoid that with this computational formula. So let me compare this formula here to this formula here. The square root is the same in both formulas. The n down here is the same for both formulas. The thing that's different is this part right here that I'm circling and this part right here that I'm circling. So this is the sum of the squared deviations. This is what? Well, if we pick apart what this part of the formula is saying, this part right here is saying sigma, so I'm going to be adding up. And what am I adding up? I'm adding up x sub I squared. So what that means is I'm going to take each of the data values, because that's what x sub I stands for. I'm going to take each of the data values and I'm going to square it. And then I'm going to add up those squares. So if these are Ethan's data values here, I'm asking you in this example to use the computational formula to recompute Ethan's standard deviation from the previous example. So for this part of this calculation, I'm going to take each data value and square it. So 9 squared is 81. 24 squared is 576. 8 squared, 64. 9 squared is 81. 5 squared is 25. 8 squared is 64. 9 squared is 81. 10 squared is 100. 8 squared is 64. 10 squared is 100. So I'm taking each data value and I'm squaring them. And then I'm going to add those up. So I'm going to add up the 81. That is 81 right there, and 576 and so on. So let me do that real quick here. So 81 plus 576 plus 64 plus 81 plus 25 plus 64 plus 81 plus 100 plus 64 plus 100. That is 1,236. So this right here is 1,236. And again, that is the sum of the x sub I squared. So in this formula here, that's what this means. Take each data value, square it, and add it up. Now again, usually the arithmetic involved here is easier than the arithmetic involved here. So what am I going to do with that? Well, I'm going to subtract. What am I going to subtract? Well, look at that part up there. I got inside parentheses a sigma x sub I squared. So inside the parentheses, sigma x sub I means add up all the data values. And then whatever that answer is, I'm going to square the result. So if I add up all the data values, we've actually already done that. 9 plus 24 plus 8 plus 9 plus 5 plus 8 plus 9 plus 10 plus 8 plus 10. That added up to be 100. So that is the sum of the x sub i's right there. So now this is telling me to take that sum of x sub i's and square it and divide by n. So for Ethan, the sum of the x sub I squareds is 1,236. That's this part. I'm going to take that minus the sum of the x sub i's, that's 100, squared, divided by n, which in this case is 10. So if I do that, well, let's do this first. 100 squared is 10,000. And 10,000 divided by 10 is 1,000. So this is going to be 1,236 minus 1,000, again, because 100 squared divided by 10 is 1,000. So that is 236. Now, 236 is the same value we got right here. So that is the same as the sum of the x of I minus mu quantity squared. So again, what I'm telling you is this part right here and this part right here are the same. They happen to mathematically always work out to be the same. So this part and this part always works out to be the same. So all I then have to do is take that 236, divide by the number of data values, 10, and take the square root, and that gives me the standard deviation. So again, if I do that, the square root of 236 divided by 10 is 4.858 if I round to 3 places. So it's the same answer. The units will be fish. It's the same answer, but if I had to do it by hand, this again is typically going to be an easier formula to use than the conceptual formula up here.